celebration of learning on Friday, which, given the hiccup of me being gone, I think is a little bit premature. So I really don't like doing them on Mondays because that sucks for all parties. So what I was going to suggest is we do it on Wednesday next week. Does that sound okay? Yeah. And the reason I was thinking Wednesday rather than Friday was just to have a little bit more space until the next one. You know, because I don't want them bunched up too much. Does that sound okay? All right, so celebration of learning Wednesday next week.
What's the last topic?
Let's see.
Will it cover all the basics?
Oh, it'll cover everything up until probably what we talk about on, definitely what we talk about today and possibly Friday, okay? Now, that said, we have covered all of the basic topics, right? So we've been doing the quote, advanced ones since, well, really since last week, okay? Well, in the Mathematica before I was gone, okay? So, though obviously the Mathematica won't be on the exam, that'll be a separate thing. Yeah, so we're getting close to the point where we'll have seen everything. Not quite, but pretty close. Right, okay, so the other, I think, good reason to not do this on Monday, just other than the fact that Mondays in general kind of suck, is on Friday, what is there? Yeah, the vaccination clinic, okay? Some of the details came up in yesterday afternoon's faculty meeting, and it became known that we have like 1,000 and something doses. And so, you know, you got an arm, we got a dose for it. So even if you didn't sign up already, through and get the text message from the state to pick a time and all of that jazz. And I know there was a bit of a snafu Monday night because they accidentally sent everybody the link to the Terre Haute registration site. But oh well, right? Stuff happens. Anyway, that's sorted out now. So if you haven't already scheduled an appointment through that thing, do it. But there will be some walk-up opportunities. So if you forgot to get on the list or whatever, stay tuned for more info from either Ann Taylor or maybe Susan Albrecht. I think she's been trying to coordinate a lot of the info blast to you guys. And so, not having an exam on Monday means that if you do kind of feel crappy right after, which is, you know, sometimes happens after a vaccination of any sort, you'll have the weekend to kind of rest. So there's a reason we're doing these on Fridays, right? So anyway, would encourage you to all take a liberal advantage. Well, I guess you can't really take liberal advantage of the vaccine opportunity. You can't be like, I'll take 2 this time, right? Doesn't work that way. So anyway, yeah, we're almost out of this crap, guys. So let's keep at it. All right, so calculus. So we're going to talk about concavity and the second derivative today. And to some extent, the problem is equivalent to what we did last time. To some extent, we've got some more lingo. So concavity, what is the definition of concavity?
Which direction?
Yeah, roughly, like that's sort of what's the word? Naive is not the word I want to use, but intuitive. Yeah. Okay, so this would be an example of concave up, and this would be an example of concave down. Okay, so roughly speaking, it's sort of a shape kind of thing. Does it look like it would be a bowl that's upside down, or does it look like if it started raining, it would be collecting water in that little part of the graph? Okay, that's not a perfect analogy, but that's one that my calculus teacher gave us back in the day. And I wonder where she is now. I mean, she's probably retired, but okay. But point being, right, it's sort of roughly speaking about the shape. The technical definition is whether f double prime is positive or negative, okay? Well, what is f double prime? It's the derivative of the derivative, right? So if we know what f prime is, and then hence we know what f double prime is, then we can figure this out. Okay, so on the sheet there, we've got here two examples of the graphs, and of course these are the same as, roughly speaking, as what I drew here, okay? Another way to say that it's concave upward or downward, okay, what does it mean for the derivative for f double prime to be positive or negative? Okay, what it means is that f prime is either increasing or decreasing. Okay, so let's say it this way. F is concave up means f prime is increasing means f double prime is positive. Okay, so which word we use depends on which function we're talking about. First, second, or zeroth derivative, meaning the original function. Okay, does that kind of make sense? Okay, all right, so if f is concave up means f prime is increasing means f double prime is positive, then what's the corresponding definition to be concave down? Right, so f is concave down means f prime is what? Decreasing means f double prime is less than 0. Okay, does that kind of make sense? Yeah? Okay, so we just have to be careful about which set of language we use. And, like, I guess it's a fair question to ask, why do we have 3 different ways, essentially, to say the same thing? Okay? Why do we have 3 different ways to say the same thing? Well, notice that each of the 3 ways is looking at a different function, f versus f prime versus f double prime, okay? So depending on which function we're looking at, then that's what tells us which language to use. Okay, the other thing is, what did we do? Like, let's sort of think about what we did last time, okay? When we wanted to know when a function was increasing or decreasing, we had to look at its derivative, right? And because of the 3 questions that are up there, being concave up, being increasing, or being positive, which is the easiest to mathematically get our hands on? Being positive or negative, right? That's something we can solve for, okay? And so, like, if we want to know about the concavity of f, that's code for, all right, we need to go down to the second derivative and figure out when he's positive or negative. Okay, does that make sense? Yeah? Okay. So now let's actually do some of this. So let's actually skip over here to let's come back to page 2 later. Why don't we skip over to page 3 and actually compute one, okay? And also we'll talk about what this inflection point thing is. Okay, so if I have the function f of x is quarter x to the 4th plus 2x cubed, okay? And I want to know when this thing is concave up, when this thing is concave down, and we'll get to the inflection point part, okay? So last time what we did was we said, well, when is this function increasing and decreasing? And to answer that question, what did we do? Okay, which are places where the derivative is 0. Then we did the number line game, and that answered the question. But we were examining f prime. Okay, here, if I want to know about its concavity, I need to do the same kind of exam, but on f double prime instead of f prime. Okay, so the number line game where we find places where something's equal to 0 and we carve up the number line and we pick some test numbers, etc., that part is all going to be the same. It's just that we're going to do it to f double prime this time instead of f prime. Okay? All right, so step 1 is, well, what the heck is f double prime? Well, what's f prime? Okay. And so what's f double prime? Okay. Good? All right, so, I mean, this one's nice and easy because it's a polynomial, right? Okay, so who do I need to set equal to 0 in this particular, for what we're after in this one? F double prime, okay? We want to know when the function's concave up or down, so that means we need to look at f double prime. All right, so I'm going to set f double prime of x equal to 0, and so we have 3x squared plus 12x equals 0 is what we need to, what we need to solve. Okay, and in this case, that factors really nicely as 3x times x plus 4. Okay, and therefore the roots of this guy are what? 0 and, careful, -4, right? Yeah, this is why you don't do math at 2 in the morning, or for that matter, 8 in the morning. Except we're doing it at 8 in the morning. Yeah, Owen, you're going to love it next fall, right? Yeah. Mm-hmm. With me, no less, yeah. So it only takes 5 credits to minor in something, so you're well on your way to minoring in McKinney, right? Diploma? Yeah, your transcript. All right, so now that I've got the, well, I won't call these critical points, okay, because that's not what the word means. Critical points are places where the derivative is 0. We're not looking at the derivative, we're looking at the second one. Okay, but these places where the, excuse me, the second derivative is 0 are going to be the places where I need to split the number line, okay? So let me draw another number line here, and let me put -4 over there and 0 over here. Excuse me. I need to put like a little mute button on here so I can cough without blowing out people's eardrums who are online. Okay, so I need to pick some test numbers. What would be good choices? Okay, -5, -1, and 1. Okay, just one representative from each of the little chunks. Okay, and I need to plug each of these into my second derivative. Okay, now, I could plug them back into 3x squared plus 12x, right? That's fine. That is the second derivative. But I'm actually going to, let's use the factored form, 3x times x plus 4. Okay, because like last time, do I care what numbers I actually get? No, what I care is whether they're positive or negative. That's it. Okay, so let's take -5. If I plug him into my factored form, well, 3 times -5 would be negative. -5 plus 4 is still negative. Negative times negative is negative. Okay, so, sorry, that's what I meant to say. Okay. Yes, negative times negative is positive. Okay, now my incompetence is documented for the entire internet to see for all time. Okay. If you could, well, you know, I was going to say you should put, like, clip this part out and put it on your fridge, except it's a video. But this is also the 21st century, so it wouldn't be outrageous that. I know, which is ridiculous, right? My favorite are like the internet-connected washers and dryers. Like, really? Well, okay, in a dorm situation, I think that would probably be really useful because it would be like, bing, your dryer is done, and you could, you know, get a text message and go take care of it. Because, or the washer is done. I mean, how many times have you guys gone to do laundry and you open up the washer and it's full of stuff that's a biology experiment at this point, right? It smells like the men's locker room. All right, anyway, so we need to plug in f double prime of minus 5, we said was negative. Okay, I'm sorry, it was positive because it was a negative times a negative, okay? Yeah, this is why I need more coffee. Okay, we're clear, right? F double prime of negative 5, we plug that in, we got a positive number, yes? Okay, so that means that F is concave up on the interval that we pulled that test number out of, which was, well, oh, I'm sorry, guys. Negative infinity up through negative 4, okay? Negative 5 was our test number, but negative 4 was the actual point where the interval got carved up. Okay, so it was the fault line, if you will. Okay, are we good with that? Yes. Okay, what do you mean? Oh, yes, sorry. Well, not yet, because we haven't tested the other two intervals. So it's possible that the function is also concave up here or here, and since we haven't tested those yet, we're not quite sure. So we're just not finished yet, right? Okay, so what else do we need to do? We need to do this exact same procedure, but with negative 1 and 1. Okay, so what happens if I plug in negative 1? And I'll let you guys drive because, as we can see, I'm a bit incompetent this morning. Positive or negative? Negative. Okay, peanut gallery agree? Yeah? Okay. Negative. Okay, so it's concave down on the interval that we were looking at there, which was minus 4 up to 0. Okay? And then lastly, what do we need to look at? 1. Okay, so what do you get if you plug 1 into that, to f double prime of 1? Yeah, this one's positive again. And so, there. Okay, so to Jake's question, where is it concave up? It's concave up on the first interval, union the third interval. Okay, when I say union, what's that symbol? Yeah, the U, okay. All right, where is it concave down? Only on that single interval. Okay, so we didn't need a union or anything there. Okay, so does that make sense? So what about inflection points? Okay, what is an inflection? Well, I'll let you guys finish writing this down. So hand on your head when you're ready. And I'm so looking forward to next semester going back to the red, green, and yellow cups. And actually, the other thing that I did before the pandemic started was it's not so relevant in a class this size because there's only 10 of you. But when I was teaching Calc 1 2 falls ago and I had, 20-something, if we want to do partner, like pair you guys up, and it's good to mix things up from time to time. So how would I assign people into different groups? Oh, well, how could I? Well, when you walk in the room, I hand you an Uno card. You got to find the matching Uno card. And if anybody got smart with me, they got to draw 4. Okay? I don't play around. Yeah, well, actually, yeah, I never thought about it that way. Or I could have one of those blank cards that you can do your own, and I could be like, lose 7 turns or something. Yeah. All right, so inflection points, okay? These are kind of like the idea of a maximum and a minimum, okay? So a maximum and a minimum occurred where the function's derivative changed sign. So a maximum, we went from increasing to decreasing, and a minimum, we went from decreasing to increasing. But in both cases, we changed from one sign of the derivative to the other. Okay? For the second derivative, we only consider, do you change sign? Okay? So, did at -4 and at 0, did I change the sign of f double prime? Did it go from plus to minus or minus to plus? In both cases, it did. Okay? And so, accordingly, we will say that those points are points of inflection. Okay, so there's really 2 parts to this. To be a point of inflection, you have to be a point where the second derivative is 0 and the second derivative had to switch sign when it went through you. Okay, so how do I know that -4 and 0 made the second derivative equal to 0? I mean, that's how we found them in the first place, right? Because we set the second derivative equal to 0, we solved, and we got -4 and 0. Okay, so they make that true. And did the concavity change at those 2 points? Yes, it went from either minus to plus or plus to minus. Either way, it doesn't matter. Okay, and so when both of those things are true, we call them points of inflection. Okay, is that okay? All right, now, because this is a liberal arts college, I'm going to get on a soapbox for a moment. What is the correct plural of point of inflection? Points of inflection. Okay, it's kind of like, what's the correct plural of attorney general or court martial? No, it's attorneys general and courts martial. No, it's not. Because what's the noun in attorney general? No, it's attorney. General is an adjective. Martial courts? Courts martial. Well, but yes, I mean, how many times have you said, like, how many of you guys watch SEAL Team on CBS? I'm totally addicted to, yeah. So, well, anyway, I'm not sure if it's quite gotten to court-martial territory, but yes, Master Chief Hayes has been charged with violating a war crime statute, basically. Yeah. And, okay. But if there were multiple court-martials, right, Yeah, if there were you can't even say it wrong, right, or correctly. Okay, whatever. It's points of inflection, damn it. Yes. Yeah, David Bournes, or however you say it. Because there's an of, right? Okay, and that's a fair contrast between the court martial or the attorney general kind of situation, okay? Well, or here's another example, aide de camp. Okay, now this one's fun because it's also mixing in a little bit of French. The plural is aides de camp, not aide de camps, right? Okay, anyway. So, let's look at this on Mathematica just for funsies. And what I want to do, once I get the window open, is, first I'm going to blow this up. Okay, so what I'm going to do is I'm going to plot, first let me just plot the original function. Okay, and I'll go from -6 to 2 here. All right, so the inflection points are places where, roughly speaking, the graph changes from holding water to spilling it or vice versa, okay? Now, at -4, does it look like to the left of -4, are we holding water or spilling water? Looks like holding, okay? What about to the right of -4 but to the left of 0? Spill. And then at 0, we go from spilling to holding. Okay, so does that, roughly speaking, make sense? Okay, now, if I look at the derivative of this thing, all right, so let me actually here just define this as a function. And then I'm just going to replace this with f of x. Okay, oops. Let me also plot f prime of x. Okay, so here's f prime. Where is f prime increasing? Careful. -6 to -4, or really -infinity to -4. Right, it's just I can't graph all the way over to -infinity. But yeah, -6 up to -4, and then again from 0 to whatever, okay? When is f prime decreasing? -4 to 0, okay? What does f prime have at -4? It has a maximum there because what's true about f double prime there? It's equal to 0, okay? How do I know that f double prime of -4 is 0 when I haven't graphed f double prime? Well, if this is the graph of f prime, then f double prime is what, geometrically? The slope of the, okay, so at -4, what's the slope of the tangent line? 0. Okay, so you see how this is kind of making sense? Right, now what's nice about this, well, it's both nice and annoying, is if you have information about any one of the derivatives or the original function, you can reconstruct the whole thing, okay? Here's the graph of f double prime, and does this jive with what we saw algebraically? When is this dude positive? To the left of -4 and to the right of 0. Was that what we had when we did it algebraically? Yes. And where is it negative? In between. Okay. All right. Good. All right. So let's flip over. I'll go back to the Elgato. Let's look at number 3 on that third page. Right. F of x is x over x minus 5. Okay. Now, what's going to be different on this one? Yeah, we got to use the quotient rule to get the derivatives. Okay, it also means what is the domain of this function? Yeah, so what's the bad point, basically? 5. Okay, so if the function's undefined at 5, its derivative and second derivative will also be undefined at that exact same point, right? That's duh. So when we carve up our intervals, we'll also have to have a carve point at 5 because that's a place where the derivatives are going to be undefined. Yes? Okay, so we just have one extra point we need to worry about. All right, so compute f prime, simplify it, and get f double prime. Okay, do you guys agree with the first derivative? Oh, thanks, Owen. You're a real mensch. There we go. Okay, negative 5 over x minus 5 squared. Yeah? And just for the sake of convenience, I'm going to write it like that because that'll make my second derivative easy. And it's only because the numerator was a constant that this is worth doing. It'd be 10 x minus 5 to the negative 3 times the derivative of x minus 5, which is 1. And so I'd get 10 over x minus 5 cubed. Okay, do you guys agree with my assessment there? Okay, so by rewriting this, that one in negative exponent form, I could have avoided using the quotient rule. And in fact, I didn't need to use the product rule because I don't need to do the product or quotient rule if one of the terms is just a constant. If you do the product or quotient rule and one of the terms is a constant, well, that's okay because what's the derivative of a constant? So it'll just sort itself out, right? Okay, so this one worked out suspiciously cleanly. Okay, that's fine. So looking at the second derivative, what do we need to know in order to split up our interval? Well, we already know we have a split point at 5, okay, because what happens at 5? Yeah, the function's undefined, okay? But what other split points do we need? We need places where the derivative is, or the second derivative in this case, is 0. Well, where are those values? What are they? Huh? Well, 5 makes it undefined. What makes it 0? There aren't any. Okay? Because we have a fraction, right, for our second derivative. When can a fraction equal 0? Only when the top is equal to 0. And the last time I checked, 10 and 0 were different numbers. Okay? So, never happens. Well, yes, if. Huh?
So the test 5 there.
Well, no, we can't test 5 because we can't plug it in. However, yeah, exactly. So we still have a split point. Okay, and I like to do more like an asymptote-y looking thing if I know there's an asymptote there. Okay, so we only have one split point in this particular case. Oh, I'm sorry. That's what I meant. This is why you shouldn't stay up until in the library working on code with guys until 21:30 when you have to be up at 06:30 the next day. Huh? 9:30. Yeah. Well, when you also got up at 06:30 that same day, and you worked the entire day. I mean, basically yesterday I had 20 minutes to pet the dog. I went to El Charro and had a burrito and a much-needed margarita, and then back to the library. So, okay. So we still need to do some test points. So let's do 0 and 6. Okay? And we need to plug these into the second derivative. Okay, so f double prime of 0 is what? Negative. Alex, you gotta have some more gusto.
Negative.
Negative. There we go. All right. And so what does this mean? F double prime, or excuse me, F is concave up, negative down, sorry, on minus infinity up through 5. That is the worst. Let's, yeah. There, that looks a little bit better. Okay. Huh?
Really sucked on that -5, huh?
Damn it. Oh, no, I got it right this time. Okay. Okay. Yeah. This is why you shouldn't stay up working on code late, because then you're incompetent the next morning. Sorry, guys. Well, the sun had partially gone down at least. Yeah. Okay, so great. And now what about at 6? What's going on there? Yeah, it happens to be positive, so F is concave up on 5 to infinity. Okay. Question. Is x equals 5 the location of a point of inflection? Why not? Because f double prime is undefined there. Okay? So to be a point of inflection, 2 things had to occur. You had to be a place where the second derivative was 0, and you had to be a place where the second derivative changed sign. Did both of those happen here at 5? No. Because the function was undefined at 0, and or at 5, sorry. That's not the same as being equal to 0 there. Okay. So you can switch concavity over an asymptote is basically what happened here. Okay. So let's go back to Mathematica. And sorry, I just want to make sure it's looking correct on the stream. Okay, and so what do I need to plot here? Well, I've already used F, so let's use G. Make sure this is actually, oh no, it didn't switch over. Okay. So what was the original function? X over x minus 5. Okay, and let's plot, let me plot G of x over the range. Well, let's do 0 to 10, okay, because that'll put the asymptote right in the middle. All right, does this make sense that it looks like it was concave down on the first chunk and then concave up on the second chunk? Yeah, does that seem reasonable? Okay, good. Okay, so just take a quick peek at number 4. I don't want to work the whole thing out right now, but what's going to be the potential issue on number 4? What's the domain of the original function? All real numbers, okay? How do you know that? You can cube root anything, okay? Right, raising something to the 1/3 power is the same as cube rooting it, okay? And you can cube root any number, including negatives, because what's the cube root of a negative? Just some negative number, right? You can't square root negatives, but you can cube root them just fine, okay? However, what's going to happen when you take the derivative of that function? Because when you take the derivative of it, what are you now going to have? You're going to have something to the 2/3 in the denominator. And the key word there is in the denominator. Okay? So what then there is going to happen for f double prime? Same problem. It's going to be undefined at 1, I think, right? Okay, because you'll have, that'll make the denominator equal to 0. Okay, so that's an issue. All right, now, let me just plot that one on Mathematica so we can get sort of some intuition as to what's going on. All right, so what was it? X minus 1 to the 1/3 power. And since we know 1 is kind of the issue point, let's go from like -1 to 3, say. Okay. This is an example of how many of your high school teachers were like, your calculator will lie to you. Yeah? All right. Well, guess what? Mathematica is not immune from that. Is that the whole graph? No, it's missing half of it. Okay, so this is a little detail about Mathematica. Huh? Kind of, yeah. Let me just plot it one other way. Okay, so now why did it do this? Well, the long technical reason is essentially Mathematica actually treats everything as if they are imaginary numbers and works, or excuse me, not imaginary, complex numbers, and works fully in that realm. And sometimes there's a little wrinkle with how you do things, like cube root is where I've noticed this. Okay, so yeah. Now, looking at the proper graph, which is the bottom one, okay, what sort of do you notice? What's going on at x equals negative, or excuse me, x equals 1? Huh? No, there's no discontinuity. Because what's the cube root of 0? 0, that's fine. So it's perfectly fine. Okay. What else? But so what else could be sort of an issue there at 1? Tangent line. One. Vertical, which means the slope's undefined or infinite in a sense. Okay, so it's been a little while, but you guys remember when we started talking about the derivative? And in particular, we talked about the idea of differentiability. And geometrically, what was the giveaway that you weren't differentiable? Sharp corners, like the absolute value function was a good example of that. Or, what did we run into here? A vertical tangent. Okay? Does that kind of make sense? So, on the last celebration of learning, right, what was one of the questions was to draw examples where, draw a graph where its derivatives, its tangent lines are positive, another where they're negative, another where they're 0. And then the fourth one was, draw me a graph where the derivative at some point is not defined, right? So what did you guys draw? Most of you drew sort of an absolute value looking thing, something with a sharp corner, Okay, but this would have been another such example. Okay, so we Gucci with that? Yeah? Okay. All right. And we've already talked about inflection points, so I think we're good there. Okay, so let's flip over to the very back, and we'll just start this, and we'll have to do a little bit of polish work on it on Friday. Because in particular, what the second derivative gives us is another way to identify maximum and minimum points. Okay? So last time, how did we identify maxes or mins? We said a max occurred when the first derivative was 0 and the function went from, or excuse me, the derivative went from plus to minus, right? Which meant the function was going from increasing to decreasing. Yes? Okay. That was a perfectly great way to identify maxes and mins, by looking at the first derivative. Okay? Another way that we could do it is by looking at the second derivative, and that's the thing on the top of the sheet here. Okay? If we have a critical point, then the sign of the second derivative at that point will tell us if we have a max or a min. So it gives us another tool in the toolbox. Okay, so does that kind of make sense? All right, so what we'll do first thing on Friday is the function that's there, we actually worked with that function last time, right? And we figured out its maxes and mins with the first derivative test. Well, we'll redo it with the second derivative test just to sort of contrast the two approaches. Okay? Does that sound good? All right, so I will see you guys on Friday. Sign up for a vaccination. It won't make you sterile or implant you with a Bill Gates microchip, or let's see what other conspiracy theories are floating around out there. Oh yeah, actually having 5G in my head would be pretty cool. So, huh?
It causes cancer.
Oh, well, yeah, living causes cancer. So, all right, well, I'll see you guys Friday.